All right, so welcome to Math 383. So what I want to do today is, I was mentioning, I've moved the lectures around a little bit so that some of the people with physics backgrounds can hopefully be here on Friday to talk about the uncertainty principle. Is I want to talk about an introduction to complex dynamics. So this is a variant of a talk I've given several times over the years. And so the goal today is to show you yet again how the material we've learned this semester can be useful and how very different the real and the complex cases can be. I will also describe, and I've already emailed it to you, the problem that converted me from viewing myself as a physicist as an undergraduate to viewing myself as a mathematician. It was problems 316 to 318 from Baby Rudin, the Blue Book, Principles of Mathematical Analysis. It was a description of Newton's method and just absolutely amazing. So some of you have already seen a version, if not an almost identical version of this lecture. If you have, you are not allowed to answer the questions today. How many of you have not seen Newton's method? So everyone else has seen Newton's method? How many people are confident that they can describe Newton's method right now? Yes. Okay, and how many people know the connections of that to complex dynamics? All right, so there will still be at least some stuff to do. Okay, so a lot of this stuff is motivated by physics or atmospheric science, by the theory of chaos. So we talked a little bit about this when we were discussing the orbits of point masses under gravity. If I give you 1 or 2 point masses in gravity, it's not that bad to describe what happens. 3 point masses in general is extremely hard. We can no longer write down a closed form solution of what happens. We discussed how uranium with over 200 protons and neutrons, just no chance of being able to deal with computations like this. Imagine, something like the weather, which is going to be even worse than uranium. So you've probably heard things like the butterfly effect. If a butterfly flaps its wings, then it can cause a tsunami in the Pacific. So we have to find this butterfly before it can flap its wings, right? You've at least heard the positive spin. So the problem is it's extreme sensitivity to initial conditions. If you change things by an incredibly small amount in a very short period of time, you can have exponentially different behavior. This is extremely bad because it means for certain problems, you have such sensitivity that you may not be able to describe what happens because you can't measure things accurately enough. Feynman has some wonderful quotes of trying to put things in perspective. Quantum mechanics is so accurate in terms of just how many decimals we can now get. It's equivalent to measuring the distance from Los Angeles to Boston to within the thickness of a human hair. And at this point, it doesn't really matter if you're doing it the thin way or the long way. A measurement that accurate is just phenomenal when you consider how many orders of magnitude this is spanning. But when you have things that depend on 20, 30, 40 decimal digits, we're not going to measure things that accurately. One of my former students works on climate models. And one of the things he tells me all the time is that a lot of these models are extremely sensitive to the values of certain parameters. And if you change them by very small amounts, you can get very different behaviors. And so you want to get a sense of how careful do you have to be. So I'm not going to go into all of the great stuff from Lorenz's paper. Poincaré, about a century earlier, looking at the orbits of planets was the first place where we really started to see this chaotic behavior. But he was running some very simple models of trying to understand atmospheric problems. And he had a printout. And he thought some of it was interesting, so he decided to rerun. And rather than start at the beginning, he just inputted the values from partway through and just had the computer start there. And very quickly, he got different results. And the reason is the computer, I think, was working with 6 digits accuracy, but the printout only had 3 digits accuracy. And in a short amount of time, that difference was enough to get wildly different behavior. And this just really drove home that some of these systems are so sensitive to conditions that small changes very rapidly lead to wildly different results. All right, so I'm going to skip a lot of this. And what I want to do is I want to talk first about dimension. So the idea is to take certain concepts which you hopefully understand quite well and put you on the spot. And how would you describe this mathematically? So this might remind you of your old geometry classes, where you have these fundamental objects that you define somehow, and then you have your axioms, and then everything follows from the rules of logic from your definitions and axioms. So does somebody want to try to define dimension? Okay, number of spanning vectors. Linearly independent spanning vector. I think when you say spanning, that includes linearly independent. Oh wait, no, you can, no, you're right, I'm sorry, you can span without being linearly independent, yes. So when you say the number, what's implicit about dimension when you say number like this? Finite. Integer. So could we have an infinite dimensional space? Yes, and so when you say number, you can say, oh, no, I'll consider different levels of infinity as acceptable. And then does it have to be integer? Can we take 3/3? Oh, well, sorry, we could take 3/3. Can we take, I had so little chance of screwing this up, right? Can we take 3/5 of a dimension? What would that mean? Now, we do know, for instance, -1/2 factorial is? Nope, not a bad guess though. It is the square root of pi. -1/2 factorial is the square root of pi. So we do have ways of extending definitions. So is there a way maybe to extend dimension to non-integer values? So for instance, does dimension have to at least be positive? And so a good definition is the Hausdorff definition. So imagine we have a set in Rn, so we have an n tuple. Then if we dilate it by a factor of r, if we get c copies, we say the dimension is the number d such that r to the d equals c. So by dilating, it means I rescale everything by a factor of c. So somebody give me a really nice shape that I can understand what it means to dilate it. Square. So if I dilate a square by a factor of 2, so if I double every point, I now have how many squares? 4. Give me another nice simple shape. Okay, triangle. Give me another nice simple shape. Circle. Which would you rather work with, triangles, squares, or circles? Which one is the bad one? Circles are bad because you want to talk about how many copies of the original do you have. Well, I'm not going to write a circle as copies of circles, but I can write a square as copies of squares, triangles as copies of triangles. You could do all of this locally. You can take a small little patch and see what's going on in that little patch. And there we would want to use things like squares and whatnot. All right. So we'll start off with one dimension. We take a line segment of length 1. If we dilate by a factor of 3, we get 3 copies. So the dimension would satisfy 3 to the d equals 3, or the dimension equals 1. If we take the square, if we triple, we get 9 copies. Dimension would be 2. I'm not going to draw what would happen in 3-dimensional space. So this is good. This mathematical definition at least reduces to what we're familiar with. But it has a chance of actually being true in greater generality. So how many people have seen the Cantor set? Okay, how many people have not seen the Cantor set? Okay, so one of the goals is to make sure that when you leave Williams, there are certain things that you can check off that you've seen. And so when you take certain classes, we're the last line of defense. We have to make sure before you graduate. There was a class one year where they did not do eigenvalues in linear algebra. And so there's lots of things to cover. And so depending on who's teaching different classes, there are some great things that just are not covered due to lack of time. There is so much you can do with the Cantor set. The way the Cantor set is defined is you take the unit interval, and at every moment in time, to get to the next level, you throw away the middle third of every interval that's left. So just skipping forward a couple of slides. We keep throwing away the middle third. So we first throw away everything from 1/3 to 2/3. Then we throw from 1/9 to 2/9, and then 7/9 to 8/9, and so on and so on and so on. So can anybody tell me what the length will be in the limit? The length will be? No, I'm not asking the dimension. I'm asking the length of the set. 0. It has length 0. At every stage, you keep 2/3 of what you have. So if you start off with length 1, in the nth stage, your length is 2/3 to the n. So in the limit, it has length 0. So if you know measure theory, it has measure 0. How many people have taken measure theory? So if you draw your little epsilon balls, you can show that its length is bounded by epsilon for any epsilon. Anybody know how many points the set has? Uncountably many. So in fact, if you look at it, we love base 2, we love base 10, we love base E, but base 3 actually has some good things to itself, to its credit. Base 3 is actually a little bit more efficient for disk storage. You can view this as if I throw away everything from 1/3 to 2/3, I'm throwing away everything that has its first digit in its base 3 expansion of a 1. And then if I throw away from 1/9 to 2/9 and 7/9 to 8/9, I'm throwing away of what survives anything that has a 1 in its second digit. So all the numbers that are left basically are equivalent to the numbers that do not have a 1 in their base 3 expansion. So if I write a number in base 3, it'll be the sum of bn over 3 to the n. Well, I can convert this, I can map this to a base 2 expansion by just take bn, which is either 0 or 2, and divide by 2, and take 3 to the n in the denominator and replace it with 2 to the n. So I can map the Cantor set to the interval 0, 1. So it's basically as many points as the interval 0, 1. This tells you that the notion of size truly depends on how you measure things, on your choice of metric. It has length 0. So on a measure scale, it's negligible. But on a cardinality scale, it's the same cardinality as the continuum. So the Cantor set is absolutely wonderful. Anybody want to guess what we should dilate it by to try to figure out what's the dimension? Not n. It's going to be a good fixed number. 3. So if we dilate it by 3, everything from 0 to 1/3 expands and becomes 0 to 1. So now this section that we're missing from 1/9 to 2/9, when you multiply by 3, becomes the missing section from 1/3 to 2/3. So if we multiply every point in the Cantor set by 3, the part on the far left third becomes a full copy of the Cantor set. The middle, which was missing, becomes now a missing interval of size 1. And then the part on the far right becomes another copy of the Cantor set, now from 2 to 3. So if we dilate it by a factor of 3, we get 2 copies. So the dimension is the log of 2 base 3, which is cut off, which is about 0.69, I'm sorry, which is about 0.63093, which is not an integer. So we now have our first example of a space where we have a non-integer dimension. And then I gave this lecture, I believe, in L functions and sphere packing last year. And one of my students actually played around with this and was able to show you can get any positive real number as a dimension of a set. So any real number can be attained through some kind of construction. How many of you have heard about what happens to the Cantor set after Thanksgiving? It becomes a flat Cantor set, right? So you can play games with what if you don't throw away the middle third every time? What if you throw away a different amount? And you can create a whole slew of wonderful examples in measure theory in terms of working with spaces like this and doing dynamics in spaces like this. Okay, Pascal's triangle, extremely famous. So what we're going to do is every time we have an odd number, we're going to put a dot. Every time we have an even number, we're going to remove it. And so if we just have the 0th row, it's just a dot. If we just have the first 4 rows, it looks like this. If we have the first maybe 8 or 9 rows, it looks like this. Does this look like anything to people? Sierpinski's triangle. How many people have ever seen the connection between Sierpinski's triangle and Pascal's triangle? Okay, so some people have seen this before. So we can extend it further. I've since fixed this. I wrote a computer program in Mathematica to just display more and more rows. You can just click on the video and watch it later if you are interested. When you are constructing more and more rows, you want to keep normalizing it so that you always display it in a region of the same size. I could, of course, just keep adding more and more rows by going further and further and further, but my screen won't take it. So I'm always adjusting so that the last row is a fixed distance away from the origin. Initially, the way Mathematica had things, it was easier to display it with the vertex at the origin and going to the right. I have since, bit the bullet and fixed it so it now starts at the top and comes down. It really doesn't matter. If necessary, just tilt your head. And you can see that as we do more and more rows, it is looking more and more like Sierpinski's triangle. Well, what is Sierpinski's triangle? You start off with an equilateral triangle, and you throw away the middle equilateral triangle when you just take the midpoints of the three sides and connect them. And then lather, rinse, repeat. So this looks like what kind of object? What have we seen that this kind of looks like? Fractal? Well, which one? I've only seen one other one today. Cantor, right? Cantor, we threw away the middle third. Here we're throwing away the middle triangle. So can anybody give me an upper bound for the dimension of the Sierpinski triangle? 2, right? This should not have dimension greater than 2 because it lives in a plane. Can somebody give me a good lower bound? 1. A bad lower bound is 0. We know it has to be at least 0. Why is it lower bound 1? Yeah, the line segment at the very bottom is never removed. So we know it contains a line. So we know its dimension is at least 1. We know its dimension is at most 2. So it's got to be somewhere between 1 and 2. Well, anybody want to tell me what we should dilate by? Last time we dilated by a factor of 3. What should we dilate by this time? 2. Beautiful. So this goes from 0 to 1/2. So if we dilate by a factor of 2, this triangle down here in the bottom left corner expands and becomes the whole thing. So this bottom triangle becomes a full copy of the Sierpinski triangle. So we have 3 triangles that each become a full copy. So if we dilate by 2, we get 3 copies. All right, so we need to solve r to the d equals c, r equals 2, c equals 3. All right, so d is the log of 3 base 2, or about 1.58496. And as you would expect, more than 1, less than 2. Of course, there's many ways you can generalize. And one of the themes as you go further in mathematics is whenever you see something, you always want to ask, well, what next? What could I do beyond this? So instead of looking at Pascal's triangle mod 2, what could I do? Well, yeah, you could do mod 3. And part of this is just issues with the computer program that was printing it out from the web. There are not white dots like this. You could look at it mod 4. You could ask, how does the factorization of the modulus affect what the answer looks like? Mod 5, and so on and so on. You could try to look at higher dimensional analogs. Is there a 3-dimensional version of Pascal's triangle? What if I start using something with multinomial coefficients? What could I get if I play games like that? One of the applications of this, which I'm not going to go into too much detail, is to coastlines. So it turns out that depending on how you measure coastlines, you can get different values for the length of the coastline. And in fact, in many settings, the length of a coastline is actually going to be infinite. It's going to have dimension greater than 1. So the standard example is, imagine you have a measuring stick of a fixed length. And so here we measure the coast of Britain using a 200-kilometer stick. And then we use a 100-kilometer, and then we use a 50-kilometer. Can anybody explain why we seem to get a larger value as the stick size gets smaller and smaller? Okay, but why are we getting a larger value? Maybe it should be stabilizing. Yes. Yeah, so when you have a jagged coastline, this allows you to follow it more closely. What country do you think might have a tremendous amount of jaggedness? Norway, right? Any fans of Hitchhiker's Guide to the Galaxy? Right. So you remember the book, you might think of the references to the Scandinavian coastlines. So you would expect maybe a higher dimension there because of the jaggedness in the fjords as you're going in and out, versus a country that is much smoother on the boundary. All right, the last one I want to do is just the Koch snowflake. And you can do this either as modification of a line segment or modification of an equilateral triangle. I'll do it as a modification of a line segment. So in the Cantor set, we threw away the middle third. So rather than throwing away the middle third, what I'm going to do is I'm going to draw an equilateral triangle at the middle third and then just throw away the bottom. So I'm only caring about the outside perimeter. So what can you tell me about the length? Well, the length is increasing by a factor of 4/3 each time. So the length is going to go to infinity. With a little bit of work, you can prove that it's actually contained in a bounded region of the plane so that its dimension should be less than 2. And when you do the calculation, you get the dimension is about 1.2. So the nice thing about this is it at least shows that not every set that has dimension greater than 1 has the same dimension greater than 1. We at least have 2 different values. Okay, it could be that these are the only 2 values that exist, but at least not everything is the same. And that there's hope that you might be able to get any possible positive real number as a dimension. All right, so now it's time to shift and get into chaos and complex dynamics. So much of math is about solving equations. The first equations you should have absolutely no trouble solving. If you do, just fake it, because I cannot bear the fact that this could cause trouble. All right, ax plus b equals 0. All right, going to assume everyone has no trouble solving ax plus b equals 0. If I give you ax squared plus bx plus c equals 0, again, quadratic formula, what's the way we normally prove that? Complete the square. You could also prove that this works by the method of divine inspiration. If I'm giving you what the solution is, well, then you can just try it. You can just look at x minus the first root times x minus the second root, expand everything out, and say, oh, good, we get ax squared plus bx plus c. That works if you happen to know what the roots are. And it becomes an interesting question to try to figure out, is there a formula in general? The key part of this is the discriminant, b squared minus 4ac. This controls what type of roots we have. If the discriminant is positive, we have 2 distinct real roots. If the discriminant is 0, we have a repeated real root. And if the discriminant is negative, we have 2 complex conjugate imaginary, so 2 complex conjugate roots. There are formulas for the cubic and the quartic. There are explicit formulas in terms of the coefficients of the polynomial. There are not formulas for a generic quintic and higher. How many have seen a proof of this theorem? Excellent. And so sometimes in a Galois theory class, maybe in an abstract algebra class, you'll prove that there is no explicit closed form solution, which is quite sad. There's a lot of things where it's absolutely wonderful to be able to write down a closed form expression for what the root is. And then if I vary my parameters, I can see how the root changes. We can't do this in general, sadly. There's a whole theory as to why. And again, whenever you're reading a paper, you always want to ask why. What is the miracle? Why could we go to this point and not further? Why can we get solutions to the quadratic, the cubic, the quartic, but not the quintic and higher? So one of the methods for solving these creates auxiliary polynomials. And if you look at the degree of the auxiliary polynomial that's created, for the quadratic, cubic, and quartic, it creates a polynomial of smaller degree. Smaller degree, I can shampoo, lather, rinse, repeat. I can keep doing this to get down to something smaller. Once you get to the quintic, when you use this method, you get a polynomial of degree 6. You're now going in the wrong direction. It's making things worse. And this gives you, it doesn't prove that it can't be done, but it proves that this method is not going to work because it's going to generate something worse rather than something better. In the old days, we didn't quite have a publish or perish mentality. People often kept their results secret, and you could challenge people for their position or for honor. And so the person who came up with a solution to the cubic actually kept it secret, so that if anybody ever challenged him, he would respond with, here's 10 cubics, tell me the solutions. Who are my computer scientists here? So there's a class of problems where it's hard to solve, but easy to check. What are these called? And this is a great example of a problem that might be hard to solve, but it's very easy to check. If somebody claims that they have a factorization, you can check and see if it's true. And you don't have to divulge your method. Now, what's interesting is, could I give you a certain set of polynomials where if you give me the answers, I can then sniff out the functional form of how it depends on the coefficients of the polynomial. So if I cleverly choose and you have to respond, could I then use that to sniff out your formula? That becomes a really interesting question as to how many polynomials would I have to give you to figure it out. To give you a sense of how challenging this could be, this is the formula for the cubic for the 3 roots. And here is the formula for one of the roots of the quartic. There is a reason why we don't make you memorize this. You could make the formulas a little bit easier. You could say, well, without loss of generality, we might as well assume a equals 1. And then you can always translate. So without loss of generality, you can assume b equals 0. You know, the x cubed term has coefficient 0, but it's still going to be a nightmare. And so the question is, how would you try to sniff something like this out? And so as an extra credit problem, imagine you have the cubic or the quartic oracle. So you can go to the oracle and give it a cubic or quartic, and it will give you the answer. And the question is, can you use that to then deduce the generic formula for the cubic? Can you use that to deduce the generic formula for the quartic? And if so, how? So I don't know if this has been done before, so I will just leave that as an open, fun problem to think about. All right. Has everybody here done divide and conquer before? Raise your hand if you have not seen divide and conquer. Okay, so divide and conquer is basically the intermediate value theorem from calculus. If you have a continuous function and you start negative and you end positive, then there has to be at least one crossing of the x-axis. There could be multiple, but there has to be at least one. So you can use this to find roots of polynomials, or to find solutions of equations. And so since people have seen this before, I'm going to just jump straight ahead. What you do is you look at the left and the right endpoint, and if one is positive and one is negative, there's a root in between. So you look at the middle. If it's 0 at the middle, you found the root. If it's positive, then there is a root between the negative and the positive. Go halfway between. If it's negative, it's between the negative and the positive, and just so on and so on. So let's take the polynomial x squared minus 3. So the roots of this are plus and minus square root of 3. So let's try to find the square root of 3. So it's about 1.732. This is one of the numbers you should just know. You should know the log of 2 base 10. I'm sorry, the log of 2 base e. You should know the square root of 4. Yes. Should also know the square root of 2. Just seeing who's paying attention. All right. Square root of 3, about 1.732. This is one of the numbers you should know. Why should you know the square root of 3? Why is that an important one to know? Sine and cosine. When you think of your sines and cosines, square root of 3 arises. That's also why we need to know square root of 2. That also arises in the sines and cosines. Okay, square root of 5 for Fibonacci numbers, I would put that there as well so you can get the golden mean. So after 10 iterations, we get that it's somewhere between 1.7304 and 1.7324. The square root of 3, sorry, it's killing at the bottom, is 1.73205. So 1.73205, it's a little bit higher than the left endpoint. The left endpoint is actually very good, but we don't know it's that good. Every time we do another iteration, what happens to the size of our uncertainty? Halves. So that means in 10 iterations, it's 1 over 2 to the 10th, which is 1 over 1024, which is roughly 1 over 1,000. And this is why in computer science, we talk about there's 1,024 megabytes in a gigabyte, but we still say mega and giga because it's almost the factor of 1,000. 1,024 is so close to 1,000. Let's just call it 1,000 in terms of the nice notations. Is this a good method? Every 10 iterations gives you 3 more digits. It's not horrible, but whenever I ask you, good relative to what? What are my other options? And so a lot of mathematics, this is the difference between theoretical mathematics and applied mathematics. In applied mathematics, we often say, oh, something exists. In theoretical mathematics, something exists. In applied mathematics, we need to find it. And we need to find it in a reasonable amount of time. Any positive integer can be factored uniquely as a product of primes in increasing order. Finding that factorization is a challenge. So 3 decimal digits for 10 iterations. So if I want 9 digits, it's going to take me 30 iterations. But all I have to do is evaluate my function well enough to know, is it positive or negative? It's not showing it here, but actually all of my endpoints are nice rational numbers as well. So I'm getting a nice rational bound, a nice rational region where it lives. All right, so the question is, can we do better? So what am I assuming about my function when I'm using divide and conquer? I'm sorry? I'm not assuming monotonic. Yes, I will assume bounded. Continuous. All we're really assuming is that the function is continuous, so we can use the intermediate value theorem. What else might you assume about a function? Well, I mean, if there's multiple roots, what you can then do is you can then refine and look at the other roots. So what else might you want to assume about your function? Okay, but please, don't use a word like that. What word would you like to use? Thank you, holomorphic, right? This is supposed to be a lecture in complex analysis, right? We got to sound highfalutin, yes? Well, if we assume that the function is continuous, then we know it's negative at one point and positive at another, then we know it has to have a root.
Yes, but are we assuming that it changes sign? Like
Sure. So if we have a change of sign, we know that there's a root. So oh wait, no, Ben is actually watching this by Zoom, so he can keep track at home. So if we're trying to find zeros of the Riemann zeta function, it turns out that there is a function that has the same absolute value as the Riemann zeta function on the critical line, but is real valued. And this function can be both positive and negative. So it turns out when this function has a sign change, you have a zero of the zeta function. And so one way that people find zeros of the zeta function is they look for sign changes of this function on the critical line. So they use divide and conquer. Now in complex analysis, the point that was just mentioned is, well, how do we know if there's a zero in the region? Do we have any way to know how many zeros there are in a region in a complex analysis? Yes, we have these formulas where if we do a certain contour integral, it will tell us how many zeros and poles there are in the region. And since the zeta function only has a pole at s equals 1, we can actually do this contour integral and we know how many zeros there are. So this is how people can say we are starting at the 10 to the 22nd zero, or we're looking at the next few zeros. We know we haven't missed any because we can actually do these contours and count. So it's a remarkable result in complex analysis that we can know how many zeros there are in play. And so we know if we found everything. And so if we haven't found enough zeros, then we might have to go back and maybe we were taking too large of a steps as we were walking. And we have to do something smaller so that we can see a sign change. All right, so what I want to do is I want to describe Newton's method. And since most people have seen it before, I'm going to do it pretty quickly. So we want to solve f of x equals 0. And what we're going to do is we're going to look at the tangent line to the curve y equals f of x. So at the point xn, the value is going to be f of xn, and the slope is going to be f prime of xn. We draw the tangent line, which is y minus the y value, f of xn, equals the slope f prime of xn times x minus xn. And we see where the tangent line hits the x-axis. Well, when it hits the x-axis, y is 0, and we'll call that value of xn plus 1, our next guess. And then just shampoo mathematics, lather, rinse, repeat. So explicitly, here is my curve y equals f of x. Here's my point x naught. I draw the tangent line, and I continue to flow along the tangent line, and I see where it hits, and it hits at some point x1. And then I do it all over again. I draw the line at x1, I see where it hits the curve, and I flow down and there's x2. You know, proof by picture got pretty close. And if we were to try to do this again, it would get even closer. And so the question is, how rapidly does it converge? For which functions does it converge? What are the convergence issues, et cetera, et cetera, et cetera. Well, if I take the function f of x is x squared minus 3, after doing a little bit of algebra, we get xn plus 1. The next guess is 1/2 xn plus 3 over xn. So whenever possible, whenever you get a formula in mathematics, you always want to ask, is this reasonable? So what would be, in a perfect world, what would be a great value for xn? Yes, square root of 3. Imagine we're fortunate enough to actually have xn equals the square root of 3. I would not want Newton's method to move me from that root. And so if we put in xn equals square root of 3, we get 1/2 of root 3 plus 3 over root 3. Oh, beautiful. It doesn't move. This is known as a fixed point. If I take a large value of xn, so I take xn equals 100, then we get 100 plus 3 over 100. 100 plus 3 over 100 is essentially 100. I take half of that is 50. I then take 50 and I would go, 50 plus 3 over 50, okay, that's essentially 25. So you can see it looks like it's going to be collapsing down to the square root of 3. What if I took a small number? If I took 1/10? Well, then I would become large and then I would collapse again. So you can start to ask, what will happen in the dynamics? How will this move? And so I've emailed you the problems from Rudin. So 316 is Newton's method applied to the square root. 317 is another way, if memory serves, of calculating roots. And 318 is Newton's method to find the pth root of a number. So again, if I want the square root of 3, I can just say, oh, the answer is square root of 3. But just saying square root of 3 doesn't mean I actually know what the square root of 3 is. I want digits of the square root of 3. So let's try to find digits of square root of 3. So if this does not make you lean back in awe, I have failed as a professor and I accept the consequences. Okay? So let's try to estimate the square root of 3. I will take as my initial guess 2, which I think we can all agree is not a particularly great guess for the square root of 3. So if I take x naught equals 2, my first iteration gives me 7/4, or 1.75. That's not so bad. My second iteration, 97/56, again, nice rational number. 97 over 56 is 1.73214 versus 1.73205. Not bad. My third guess, 18,817 over 10,864, 1.732050810 versus 1.732050875. So we're off by about 0.0000000025 roughly. After 3 iterations. And we have a rational number as an approximation. With a denominator, that's not that bad. If you do 5 iterations, I'm not going to bother reading the fraction anymore, but look at how deep we have to go before we finally see a digit that is not the same as the corresponding digit of the square root of 3. Amazing how well this works. So it's not just that it gives you an approximation of the square root of 3, it gives you an incredibly rapidly converging approximation. In the problems that I sent you from Rudin, which I strongly urge you to do, you basically show that every iteration doubles your number of decimal digits of accuracy. So you divide and conquer, plotting around every 10 iterations, you get another 3. Newton's method, every iteration, you double the number of decimal digits. Who here has a calculator? All right, so try to calculate the square root of 3 on your phone and just see how many digits you can give me. Are you using your phone or your computer? All right. What program are you using? Can we just a regular calculator program?
No, I think you meant like an actual book calculator.
No, I want like a phone calculator. Because your computer calculator, if you're using Wolfram Alpha, you can get a huge number of digits. But I'm just curious, what can you get on a phone before the 12 digits? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So somewhere around here is where you're going to be breaking up on a phone. And we're able to do well more than that without any trouble. Why does Newton's method kick ass relative to divide and conquer? Why does it do so much better?
Well, in divide and conquer, we have no information about the function inputted other than there's a zero somewhere in the region. Whereas here we're using a derivative.
Good. So we're using more information in Newton's method. We're using differentiability. We're using holomorphicity. In divide and conquer, we're just using continuity. It's not surprising that we can do better, but we now need a differentiable function. All right, so let's play a little game. So we're going to color points. I'm going to look at the function x squared minus 1. We'll color you blue if you converge to the root at 1. We'll color you red if you converge to the root at minus 1. Anybody want to tell me how we color the line as we play the game using Newton's method? Who's colored red, who's colored blue, and who is purple? The battleground numbers. So what numbers do you think converge to 1? What numbers do you think converge to minus 1 under Newton's method? And what numbers do you think don't converge? Yes.
All the negative numbers.
Yeah, all the negative numbers. And in fact, if xn is negative, this stays negative. So that doesn't prove that it converges to minus 1, but it does prove it doesn't converge to 1. Similarly, if you start off positive, you stay positive. So it's not unreasonable to expect that everything that's positive goes to 1, everything that's negative goes to negative 1. And what about 0? Well, we can't divide by 0. So 0 should be uncolored. Can somebody give me a nice way of describing how you determine which number you converge to? You converge to the number that is so if I'm trying to determine which root I converge to, when I use Newton's method, I converge to the root that is closest. What a wonderful property, right? I go to the root that's closest. So let's see what happens if we go into the complex plane. And again, a theme of this class is that when you look at the complex version of a problem, it is often completely different than the real version. So let's take the polynomial x cubed minus 1 equals 0. We could, of course, use the cubic formula, but we could also do polynomial long division, right? Can somebody give me a root of x cubed minus 1 equals 0? 1. So we factor out x minus 1, and now we can just do the quadratic formula on x squared plus x plus 1, and we get our 3 roots. At 1, negative a half plus I root 3 over 2, and negative 1/2 minus I root 3 over 2. So I've drawn them in the complex plane. It's okay if your guess is wrong. How would you color the plane? We have our 3 roots. We use Newton's method. Which roots do you think converge to blue, to red, to green? It's okay if you're wrong, but what would you say or what would you hope? Yeah, the ones that are closest. So I divide the plane into 3 regions, and then whatever root you're closest to, you converge to. Here is what the plot is. And so it's a little bit hard to see because the link is in blue, but there is a link below Newton fractals that you can click on YouTube and actually watch what happens as you zoom in on this. And this is a wonderful example of extreme sensitivity to initial conditions. Now you have these giant basins where things are as you would expect. In this region, I'm converging to blue. Blue is the closest root, that's great. But as we get near the boundary of the regions, strange stuff happens. If you look really closely, you see that there are these black regions. Computer's basically just giving up. All right, you can zoom in a little bit. How many of you know Horner's algorithm for evaluating polynomials rapidly? So I actually coded stuff like this when I was in high school. And again, this is more than 25 years ago. It was a long time ago. And so any savings I could do in computational time was necessary to try to get reasonable plots that we could zoom in on. I think I actually still have an old computer at home where I can still run these Pascal programs. But when you are looking at something like this right on the boundary, it is so sensitive to the initial conditions, it's hard to tell. But you have this incredible self-similarity as you're zooming in. And we saw this when we started off with the discussion of fractals at the beginning of the day, where when you expand it, when you dilate it, you get in your copies again. You can see these copies of this region over here. You can see interesting behavior going on. There are a tremendous wealth of questions that can be asked about the shapes that come here. And again, extremely small changes in the initial conditions can change where we go. In this little region over here, we go between red, green, and blue. And so you're over here, the blue is the furthest route away, but if you change things by an extremely small amount, you can go to blue. What this tells you is that there are certain situations where you have to be very concerned about the conclusions or the advice people are giving you if the system depends crucially on extreme knowledge of values. When my father was getting his MBA, he was taking a class with a very theoretical professor who gave them an equation involving 46 variables to describe what they should do in any business situation. And my father, of course, is a nice, polite, kind person, and in a very respectful tone, tried to engage the professor in dialogue using sentences such as, I don't even know the values of some of these parameters for my own company, let alone my competition. But isn't it a beautiful equation? So, the equation might have been beautiful, it might have been accurate, but it was useless because there was no way to evaluate things. When you are doing anything in the real world, you want to try to figure out which quantities do you care about most, which ones are going to have the most impact on your conclusions. And those are the ones you're going to want to measure in the greatest detail. So there's a lot of stuff that you can do. It is against the law to mention fractals without talking about the Mandelbrot set. So, just very briefly, we can look at various functions. So let's look at different numbers, complex numbers C, and I'm going to define a map, and it's going to take U as an input, and it's going to return U squared plus C. So if I start at 0, I get C, then C squared plus C, then C squared plus C squared plus C, and so on and so on and so on. And I can look at this set, and I can ask what inputs or what choices of C give me something that stays bounded as n goes to infinity. So can somebody give me a value of C where this is going to stay bounded as n goes to infinity? 0, right? When in doubt, always try being the smartass. Try looking at the most extreme case you can. Can somebody give me a value of C where it will go to infinity and it will not be bounded? 1. I would have probably chosen 2 just to be safe, to just have something that's clearly going. 1 also works. Okay. So the question is then, which points will things be bounded? And so here is the Mandelbrot set. If you use Mathematica, it has a lot of these things already built in. You can start zooming in on different sections, and you can see copies of the Mandelbrot set as you zoom in. There's lots of fun pictures online where you choose a region, you zoom in, and you zoom in, then you zoom in, and you keep zooming in, and you keep seeing the same set. I've got links to a bunch of them. They have some extremely interesting figures as you go deeper and deeper and deeper. The colors are related to how quickly you escape. And then there's all these different questions you can ask, is the Mandelbrot set connected? What can you say about dimensions of something like this? How the hell do you do a calculation like this, with enough precision to actually trust what you're getting out? It is also a requirement that you have some kind of cheesy soundtrack when you are doing all these Zooms. So depending on which version you have different things that you can listen to. A lot of different links if you really want to see some stuff about this, but it's truly, truly impressive. So I think we have 1 minute left. So why do we care about stuff like this? If small changes can lead to wildly different behavior, what does this mean for a lot of the models that we have going around that are leading to predictions? And again, giving this in a classroom where we have everybody who is here masked and some people who are not here because they weren't feeling well, and in this era, we have to be extremely careful. And we have to look at what policy should we have? What are the consequences if we're wrong? What are we giving up? We were fortunate. We were one of the schools last year that still had in-person classes, where a lot of people across the country, they had their entire college year fully remote. And so you have all of these models that are going out there that are making predictions. How much can we trust these predictions? How sensitive are these predictions to the values of certain parameters? And if so, how much effort should we make to try to get good estimates of those parameters? All right, so this is a good place to end, to just give a little bit of a sense of application of complex